Hello again. I was cut off just a hair at that last section 2.1. But in this particular section, we're going to expand on limits. In this particular case, we're going to look at infinite limits or limits at infinity and how to, the algebraic manipulation that we did. And there were some cases where the limits did not exist. And we're going to use that same type of algebra to locate vertical and horizontal asymptotes. So there are some situations or possibilities where the limit as x approaches a, or some constant of f of x, where the limit does not exist. And there are some cases when the limit becomes very large or very small, and so we say the limit is approaches infinity as x approaches a. And we use this guy right here, this little sideways 8, to describe infinite behavior. So let's take a look at one example. Here we have a rational function. F of x is equal to 1 over x minus 1. So as x approaches 1, the function is discontinuous. As x approaches 1 from the right, the values of f of x are positive and they become very, very large. And so as x approaches 1 from the positive end, which means from right to left, okay, we say that the limit of that function approaches infinity right here. And infinity is not a real number. The limit above does not actually exist, but we are going to use the infinity symbol to describe the manner in which the limit fails to exist, and this is called an infinite limit. So that is the definition of an infinite. Okay. So the previous slide we talked about as x approaches 1 from the right, and that is this line right here. And so this is x approaches 1 from the positive side. And in this slide, we're going to talk about as f of x approaches 1 from the negative side, and that's this side over here. And from the negative side, that is from the left to the right. From the positive side, it is from the right to the left. And you can see that as it approaches 1, going right to left from the positive side, this goes to positive infinity. And here from the left, we can see that this graph from the left to the right, as x approaches 1 from negative infinity, goes to negative infinity. And so you can see that the limit does not exist. However, you see this dotted line right here, and this is called a vertical, because it's a straight line, asymptote, and we're going to talk about that in our next slide. That vertical line, x approaches a, is a vertical asymptote, and you can see that even though the function does not have one limit, right, as x approaches 1 from the right, or from the positive side, it goes to positive infinity, and as x approaches 1 from the left or the negative side, the function goes to negative infinity. But they both approach this vertical line, or this vertical asymptote. How do we locate vertical asymptotes? Great question. If a function f is continuous at x equals a, then the limit of f of x is equal to the limit from the positive side, which is equal to the limit from the negative side, and it's equal to just plug in that constant into the function, just like we were doing in section 2.1. These limits are finite, and notice down here, a polynomial has no vertical asymptotes. Let's take a look at this slide. Vertical asymptotes of polynomials. Polynomials have no vertical asymptote. Let's keep going. However, there are vertical asymptotes of rational functions, which was the function that we're looking at. F of x is equal to 1 over 1 minus x, I believe. And so a rational function is discontinuous only at the zeros of its denominator, in this case when x equals 1, right? This function is discontinuous. This is a simple procedure for locating the vertical asymptotes of a rational function. Here we see that if f of x is equal to n of x, which is just calling it the numerator, over d of x is a rational function, then d of that constant is equal to 0. Then the line x equals c is a vertical asymptote of this graph. However, if both the denominator of that constant is equal to 0 and the numerator is equal to 0, there may or may not be a vertical asymptote. Okay, that's the second one. Oh, and let me clarify, for this first one here, if the numerator divided by the denominator is a rational function and the denominator is equal to 0, then x equals c is a vertical asymptote. So for this function, that vertical line that you saw, the vertical asymptote is at x equals 1. All right, so let's take a look at another example. Here we have this function f of x is equal to x squared plus x minus 2 all over, so this is what's called the n of x. Let's take all that information from the previous slide, and this denominator x squared minus 1 is equal to d of x. So there is behavior. We're going to describe the behavior of f at each point of discontinuity. We're going to use positive infinity and negative infinity when appropriate, and we're going to identify, all of the vertical asymptotes for this function. So let's take a look at something really quick. We see that n of x is equal to x squared plus x minus 2, which is this top function. We're going to call that n of x, okay? And the denominator is equal to x squared minus 2, and that's this guy right here. So again, denominator, let's make sure we label everything correctly. We're going to factor the denominator. If you look at this is a difference of two squares. This is a square, x squared, and the square root of 1 is just 1. So it's called a difference of two squares. You learned that in your algebra course. And we can factor this x squared minus 1 into x plus 1 and x minus 1. And it has two zeros. Here at x equals negative 1 and x equals 1. These are points of discontinuity. Okay, so since the denominator at as x approaches negative 1 is equal to 0, and that's this information right here, and the numerator at x equals negative 1 is equal to negative 2, it is not equal to 0. Our theorem tells us that x equals negative 1 is a vertical asymptote. So that was simple. You just have to use the property and it can tell you what your asymptote is. Now let's consider the other 0 when x equals 1. Okay, so if you remember in this slide, for this particular this top part right here, we're dealing with the first 0 at x equals negative 1. Okay, and now for here, we're going to deal with that second 0 at x equals 1. Now, in this particular case, the numerator of n equals 1 is 0, and so this theorem does not apply. We are going to use algebraic simplification to investigate the behavior of the function at x equals 1. So in this case, notice we are going to factor this top portion right here, And whenever you're factoring, I'm going to take some time to do this. What factors of negative 2 add and give you positive 1? And so the only factors for negative 2 are, it was right here on the slide, the only factors of negative 2 are negative 1 and 2, and positive 1 and negative 2. But which one of those add and give you positive 1? Well, that's this guy right here. Oops. That's this guy right here. Negative 1 plus 2 is positive 1. So negative 1 and positive 2 is how they get these factors right here, x minus 1 and x plus 2. So whenever you're trying to factor a polynomial like this, you want to look at your c right here. So if you remember, it's ax squared plus, oops, that doesn't look like x, plus bx plus c. You want to take your c and you want to look at what factors of c, multiply and give you the c that they have, and then add and give you this coefficient b right here. And so that's what we did there. And then again, we're going to factor x squared minus 1, and that is the difference of 2 squares, so it's x minus 1, x plus 1. But notice this right here cancels. And so now we're going to plug 1 in. So 1, right, plus 2 is 3. And 1 plus 1 is 2. And so the limit exists as x approaches 1. It does not have a vertical asymptote, but the limit is 3/2. So we can see the graph here. Notice that there is a point of discontinuity here at x equals 1. We have a vertical asymptote at x equals negative 1. And this is the graph of this function right here. It is always a good idea to, even though you have a function, to graph it. You can use Desmos or whatever, maybe if you have a graphing calculator. It's a good idea to look at what's happening in the function before you continue. All right, so limits at infinity. We use infinity as a symbol to describe the behavior of limits. Sometimes we'll write x approaches positive infinity, and we'll do x approaches negative infinity. So in the previous slides, we were saying x approaches some constant, or x approaches a. But what happens to a function as x approaches infinity? So we are going to begin our consideration of limits at infinity by considering power functions. So a power function is x to some power, right, like x squared, x cubed, as x approaches infinity. Now that's a pretty simple, if you just put in a number in, let's say, an x squared function, if we take the limit of x squared as x approaches infinity. Well, if you put infinity and you square it, well, you're just going to get some more infinity. All right, so let's take a look at the reciprocal of that function. Now, if you put in as x approaches infinity here, 1 over infinity, well, that's just 0, right? As the function will approach 0 as x increases without bound. So this figure illustrates the behavior for both x squared, which is this guy right here, and 1 over x squared, which is this function to the left. So power functions in general, if p is a positive real number and k is a non-zero number, then the limit as x approaches infinity for some number k all over the function x to the p, that limit is equal to 0. And as some number k times as x to some value p, as x approaches positive infinity or negative infinity, again, you have plus or minus infinity depending on, what that function looks like. All right, so what about limits at infinity for polynomial functions? I will let you read through this here. It's not too much information, but I want to take my time and go over the problems with you. So limits at infinity and horizontal asymptotes. All right, so the line y equals b, again, a horizontal asymptote is this way, just like my pen. Horizontal, okay? Vertical, if it's standing straight up, horizontal, if it's, ooh, it's weird, sideways. All right, so a horizontal asymptote. We talked about vertical asymptotes, but we're also going to find a horizontal asymptote where y is equal to b. And the limit as x approaches negative infinity is some value b, and the limit of f of x as x approaches positive infinity is some value b. That's its definition there. So you can see on this particular graph right here that although it gets really, really close to both +1 and -1, it never quite reaches those values. And so this graph here has an horizontal asymptote at x equals 1. I'm sorry, y equals 1, which is this guy right here, and y equals -1, which is this guy right here. All right, so here are the rules for horizontal asymptotes of rational functions. If, notice, let's take a look. Here is our rational function right here. And let's take a look. The numerator has a power of m. See, m minus 1, right? And the denominator, this is, okay, so this is n of x right here on top. The denominator has a exponent of n, see n right here, n minus 1, etc., all the way down to b sub 0. So if the exponent for the numerator, so if m, that's the exponent for the numerator, is less than n, which is the exponent of the denominator. So for example, if you have x squared over x cubed, then the limit of your function is 0. Okay, so again, in order to do these problems, you have to just have these rules with you. So the line is at y equals 0, and that is a horizontal asymptote for f of x. Now, if the exponent of your numerator, m, is equal to the exponent of your denominator, n, then the limit is the coefficients of a over b. So, which is these first coefficients here. So let's take a look at an example. If f of x is equal to 2x squared all over 3x squared, then the limit is 2/3. Okay, now, and your line is at y equals a over b. See, a over b. Now, if the exponent of your numerator is greater than the exponent of your denominator, you do not have a horizontal asymptote. And so for number 3, let's bring that up here to the side with that, follow that arrow. And so if you have, for example, x to the 4th all over x squared, then this does not have a horizontal asymptote. All right, so let's take a look at cases 1 and 2. A rational function can have at most one horizontal asymptote. Notice that the numerator and the denominator have the same degree here. And so in that case, we're going to use case number 2, and we're going to, the horizontal asymptote is equal to the coefficients of those first two values, and you have a horizontal asymptote at 3/2. Not too bad. All right. So let's take a look at these examples. Find the horizontal asymptotes of each function. You can see that the the exponent of the numerator is 4, and the exponent of the denominator is 6. In this case, this is case 1, where m is less than n, and so you have a horizontal asymptote at y equals 0. Not too bad, right? And in this, is it going to add? Okay, so now I added all of these things in here, but let's take a look at this bottom case, case B. You can see that the exponent of the numerator is 5, and the exponent of the leading variable on the denominator is 3. And in this case, m is greater than n, and there is no horizontal asymptote. You can see that here, no horizontal asymptote. So that's an example. All right, that is section 2.2, and I will move on to the next section, which is really important, derivatives.